All right. So today we'll talk more about concurrency. We'll go through a few different types of locks, just to see how locks can be implemented differently. Try to get into condition variables, see how that's used in x86. I think we've done that to some extent, but we'll see how the implementation in x86 kind of mirrors what a condition variable tends to do in user space. And then perhaps we'll get into some concurrency problems. Before that, any questions on the homework? Yeah?
So when a process exits, so in the console, sh, it begins. That means it wakes up, and we can type something in console and run new command. So how that thing happens? So getting back to console.
So how does sh know that everything's finished?
Yeah.
Sh is waiting. Let's take a look at the code.
There is a command to wake up sh. It starts.
There's no command to, well, okay, so why don't we take a close look at what's happening? It's a good question. So in sh, we have, after our fork somewhere, here. So after every fork, here's a normal command. We fork and then we wait for that process that we just started to finish. In every other case too, you see here, this is a pipeline. So we're forking twice, but we're waiting for both of those two children to finish. So sh explicitly asks the OS to hold off until all those children are done. If you put an ampersand after, I think sh, yeah, here, sh supports that too. If you just say the command and ampersand, that means you want to run it in the background. So now sh will accept input right away. So how does that work the whole way? Well, this wait, it's a system call. So we can take a look at syswait. Well, so actually, why don't we do it the whole way? So syswait doesn't do much. It just calls wait. Well, let's see what that does. Here. So we're waiting forever. Right? And then we look for any child that was ours. Let's see. If it's not, yeah, if it's ours and it's a zombie, then we clean it up and then we return. So we're waiting forever for some child to die, and we clean up after them and then return to user space. So that's what the wait is doing, really. Does that make sense?
And when it wakes up, so then it accepts new comments.
Yeah, of course. So sh is just a little loop that is reading a line. Well, let's look at the main. Probably in here. Yeah. So this is the sh loop, right? Gets a command, and then it does something with the command. Run command. And then, it's done with that, so it goes over again. That's all. Pretty simple. Yeah.
What might cause sh to reload, in the first process to reload, if another thread has started running?
You're having a crashing problem. I see. Let's see. So sh restarting, that is not what's happening, I think.
It's not sh. I think it's starting from init because it's printing the CPU information and then it starts.
Oh, okay. Yeah. So this is not a process doing anything. This is the kernel doing something illegal, but it's not catching it itself. So sometimes you get a panic message, right, when the kernel detects that something's wrong. In this case, you're doing something that's so wrong that the kernel didn't even get to print out the panic message. So that could happen if you execute an illegal instruction, perhaps. If you try to just run code from somewhere arbitrary. Oh, this is probably a good one. If you try to jump to an address that is not even mapped in, that might cause a problem. Yeah, I'm not exactly sure where, like, what would not cause an exception, which x86 catches. This is all up to QEMU, really. Like, maybe QEMU figures it's not worth it for some of these errors. I'm not sure. A good way to debug it is probably put out some print statements, or when it crashes like that, you can't even see what is printed out.
Yeah. So, and the problem is, if I want to put a debugger in any of the places, I mean, I'm not even sure where where is the LLS instruction of error occurring to put a debugger before it.
There are not that many places, to be honest. It's probably happening when you're returning from an interrupt.
You can always say backtrace in GDB, it's just BT, and then it'll show you the stack trace spike after.
Yeah,
Yeah,
not so much.
Sometimes.
Not when QEMU has restarted on you.
Yeah, right, okay.
You have to have
Right.
an intact stack in order to do that. So you also cannot do it if you return from the kernel into user space. You've lost the kernel stack trace, and
Yeah.
yeah. So it just goes up the stack, really, GDB. But yeah, GDB is fantastic for almost everything. Okay, yeah. Other cool little debugging tricks. Sometimes a while true loop is really handy, so that it just stops, right? Whatever it was doing. So you want to make sure it got to here, so then you can put print statements before, that sort of thing. Sometimes I put a breakpoint. Sometimes, for example, maybe the trap.c, like you don't want to put a breakpoint in trap.c because it happens so often, right? So that's no good. But sometimes you know that the next interrupt is going to be the one you're interested in. So perhaps if you've first made a system call so-and-so, then you really want to see what happens in trap. So in that case, you can first put a breakpoint in the system call, and then once you're in there, now you put a breakpoint in trap.
That's what I normally
And
do.
that sometimes helps. Yeah.
That's what I was trying to do, but except this time around, I'm not even like, I'm not entirely sure where it was having.
Yeah.
But that's what I normally do.
It'll take some fiddling. Okay, any other homework questions? Oh, okay. So let's talk briefly about some types of locks. So generally, I think every lock that matters will be using an atomic instruction. The two atomic instructions that really matter would be compare and exchange, which sometimes is called test and set, sometimes called compare and swap. Let's see. So it's test and set, TAS, compare and swap, CAS, or compare and exchange. You may run into these in, systems programming interviews. And so I'm just saying this because if someone asks how many CASs are there in this kind of synchronization operation, you'll want to know what it is. Okay, so to implement any sort of reasonable lock, we need one of these atomic instructions, or there's increment. All of these would have to be atomic. All right, but there's many different ways that we can implement locks, and it depends a little bit on the context, which lock we should be using, and sort of why one lock might be faster than another. So I thought we'd take a brief look at some alternatives. So the most easiest types of locks. The easiest one is a spin lock, sometimes called test and set, because test and set spin lock, because it basically does while try to set the lock, try to lock the lock. Let's see. Right, like that. So your compare and swap test and set or compare and exchange. Basically, you say it, if the lock was unlocked, make it locked for me, and then tell me what happened. It's done in one fell swoop. So we keep trying until it didn't work. These operations, they take a while. They'll take hundreds of nanoseconds, sometimes more than that. But generally, they do return relatively quickly with a failure if the lock is already taken. So a spin lock has this disadvantage that it uses a lot of CPU power, wastes CPU cycles. Right, if the lock is taken, we keep spinning and doing these expensive operations. In part, that's using a lot of energy, which is important on a battery-powered device. And in part, if we had something else we could be doing, this thread doesn't have anything else it could be doing. But there may be other threads that could use the CPU for something useful. Why do I say that this thread didn't have anything better to do?
It's already waiting for a lock.
Can't it just start doing something else?
Since it's included in one thing.
Exactly, yeah. So in almost all cases, the assumption of the programmer is, I try to acquire a lock, it'll stop until the lock is acquired. And so if we start doing something else, it gets really confusing. That's no good. There is something called a tri-lock. That's a spin lock without the spin. So here it just says, no, didn't work, and then you move on. So this could be, so then you would say like, oh, if try lock, lock, the lock, to the critical section. So this is not something you could generally use very effectively, right? Because critical sections tend to be doing things that are important. You want this done. But sometimes, say you're a garbage collecting thread. You know, you're running in the background, and you have a lot of different garbage to collect, and you don't really want to wait, and you don't want to bother anyone else who's using this lock now. So you just try collecting this garbage, but if the lock is held, then you move on, try something else, and maybe you come back to this later. And so that can be convenient. So if it's not something really time critical, or where the ordering is important, you might want to use a try lock. This one has very different semantics from all the other locks, so I really should, like, it's not a lock, it's a try lock. Whereas all the other locks we're going to talk about, they're all normal locks. Okay, so why would anyone want to use a spin lock, do you think? We should talk about disadvantages and advantages of every type we got here.
Easy to implement.
It's really easy. That's good.
It'll run on the first possible CPU cycle the key is available.
How do I write that short? It is,
Unlock as soon as possible.
actually, it's not quite true that it's as soon as the lock is available. Well, maybe we'll see the detail in a little bit. So yeah, it's quick, let's say. So it's not sitting around doing a lot of other stuff, a lot of overhead. Basically, we're just trying, and eventually it works, and then it's great. It's maybe it's quick in two ways. Maybe we say, maybe responds quickly when lock is freed, but also the fast path is very fast. By fast path, I mean there's two options here, right? It's available or it's not available. Right? So if the lock is available right now, is one instruction, right? Compare and exchange, done, moving on. And we don't need to do anything else when we got it until we want to release it, and then it's one assignment. We just say set the lock to 0, and we're finished. So the fast path is really fast. Unfortunately, If you have a lot of threads, if you have a wide multi-core machine, there's also going to be a lot of fighting over the cache line that holds the lock. A cache line is a 64-byte chunk that always travels between the cores. Whenever you do a write, even if it's just to 1 bit, you always request a cache line of 64 bytes, you change the bit, and then later on the cache line will move around. The granularity of writes are always 64 bytes under the covers, but you don't actually see that, except in performance. Okay, so another disadvantage is that there's a lot of congestion. Basically, you have this atomic instruction, it tries, so it fetches the line. Okay, let's back up a little bit. One thread is holding the lock. Another thread wants the lock, but the first thread is still holding the lock. Other thread wants the lock, so it tries. In order to read from this, read the lock state, it needs to get the cache line over. I should draw it. It'd be good to, oh, look at that. I even have an excellent drawing right here. Okay. So in this case, we have 8 cores, 4 on each socket. It's not important, but let's just have it travel between. Here's our lock. Let's just have the lock travel between sockets in this case. So the lock is currently held by this core. Core is doing its critical section. While it's running its critical section, the CPU doesn't really know that it will be releasing this lock later, because CPUs, they don't know about locks. They know about atomic instructions. That's it. So we've made an atomic compare and exchange to this. At some point, it became locked. And now we're running a critical section. And now someone else goes and tries to acquire this lock. What's going to happen is it will say, oh, I need exclusive access to this cache line because I'm going to write to it. So it'll move the cache line over to the core that's trying to get the lock. And now it's on the other side. Of course, it'll see, oh no, I couldn't do it because it's set to 1. But now it's on the wrong side, and this takes a long time. You can only go across this one about 5 million times per second. So it's a relatively slow connection. Okay, so now it's on the wrong side, and maybe this guy is trying to release the lock. Right? If that works out, that's great. That the lock travels over, and now we're let's see. So now we can do about, like these round trips, we can do about 2.5 million of those then per second, right? But if we're unlucky, it wasn't the next one to get the cache line. There's some random ordering in which, who gets it next? It's not like there's some nice big queue like that. There's probably a whole bunch of different queues and there's some randomness to it. But this core got it instead. This one's trying to take the lock, right? And now he's trying to take the lock. And now this one's trying to take the lock. And then it moves over here, trying to take the lock. And it's not available, right? So they're all failing. And this one's trying to release it. Eventually it releases it, right? And now finally people can get stuff done. So this is what I mean by congestion on a lock. There's a lot of useless work by all these threads trying to acquire it when it's not available. Yeah.
And the time between each one of those passes is an entire timer interrupts worth of time, right?
Oh, no. This is on sort of an instruction granularity. The unfortunate thing is the links between cores within a socket. And by a socket, I mean one of these chips that sit on a socket on a motherboard with hundreds of pins. That's a socket. Within one socket, there's multiple cores on the chip. Inside of there, at least in our recent measurements, it's about a 70 nanosecond latency on the link. So to travel one way takes 70 nanoseconds. That sounds like not so much. Right? But unfortunately, you can execute, maybe 200 instructions in that time. More, actually. There's about 200 cycles in that time, and you can usually run a couple of instructions per cycle. So now we're talking, 400 or 500 cycles for one way on this thing. And then it gets worse because this interconnect that crosses on the motherboard between the two CPUs, and sometimes you have more. This one is even slower, so we've measured it on recent machines to about 200 nanoseconds. So you can only travel across this one 5 million times per second. That's really slow. You can run 5 billion instructions per second, so you really don't want to be spending a lot of time bouncing back and forth over this thing. And it actually does really collapse the throughput of locks. So this was observed a long time ago, before multi-core CPUs even existed, but at least when you had multiple chips on one motherboard. So people start thinking about how can we make this a little faster. Actually, before we go to the faster ones, let's think about the other one, which was called a wait lock, or Q lock. So that's the one we saw last time. Basically, instead of trying to acquire a lock with an atomic instruction, well, maybe it's a little bit of both, but instead of trying and trying and trying, when you see that this lock is not available, while lock is not available, sleep until lock is available. Right, there's your require, and then the release looks like set lock to available, wake up sleepers. All right, so in this case, there's almost no fighting. But that's awesome. So now it's going to be really efficient, because in terms of the cache coherence, right, it'll be really efficient because there's never anyone trying to get the lock when it's not available, or at least very rarely. Like when one new thread enters, it'll try once, it fails, and then it'll just sleep. So the advantage here, it's very low congestion. And what do you think, what might be disadvantages of this approach?
It takes a long time before you actually get the lock. You might be sleeping for a very long time.
Well, that's true for normal locks too. If no one's releasing the lock, right, then you have to sleep. Well, sleep or spin, but either way, you're not getting anything done.
It's unfair to the sleepers, because in order they are requesting the lock, that order is not moving.
Interesting. Unfair to sleepers. It's a very good point. So, if the lock is available, we're coming in and we get it right away. But if we don't, then we go to sleep, and now some other threads that might try to acquire the lock while we're asleep. We didn't yet wake up, let's say, because this here will take a little while. The wake up requires the scheduler to get in play, and so on. It's a very good point. Well, what about this? Is this fair? Will it be like? Will it roughly be that that threads acquire the lock in the order in which they started trying? They're all just spinning, right? Spinning, and then there could be some fairness in the order in which this cache line moves around, right? But if you're trying to be perfectly fair, now you might have, let's say that this one came in first. And first of all, it's very hard to even establish in which order these requests came in, because then you have to communicate trying to establish that. But let's say you could. In the worst case, you might end up with the lock going every time going across this long interconnect, right? It'd be better if you could go a little bit in here and then go over a little bit in here, right, and so on. So there's a direct trade-off there between fairness and efficiency. But yeah, it's not inherently fair. Like even a spin lock is not inherently fair, but I think it's a very good observation that a wait lock is even less fair. Something we've observed, at least, is so pthread mutex, the normal mutex lock, that's a wait lock. And I think they spin a little bit, They don't just do a try lock, let's say, and then go to sleep. They spin for a little bit perhaps, and then they go to sleep. Using a kernel, well, a system call is called futex. Futex allows you to specify sort of the compare and swap sort of thing. You can say like, let me sleep until this thing, or if this thing is still locked, then let me sleep. Maybe we'll look at that a little bit later. But basically there's some kernel support for efficient implementations of these wait locks. It's called futex. Efficient and safe. It's hard to make it safe, actually. Okay, so anyway, there's some unfairness. Anything else that's not so good about a wait lock? It's a slow, fast path. Let's see. So if the lock is not available, well, if the lock is available, we go straight through it. That's pretty all right for a fast path. But on the release side, there is a wake up, and that's mandatory. It's not like we can just skip the wake up, because then you might have some threads sleeping forever. So that's right. I think on the fast path, the wake up is a slowdown. Why would that be slow, though? What does it take to wake up some sleepers? Say we're in user space. You need a system call, yeah. So wake up does a loop running through all of the processes. You can do a little bit better. You could probably have a linked list for this particular lock, perhaps. Right? So you don't have to loop through all processes in the whole system. But at least you need a system call, and then you need to kind of traverse the set of waiting sleepers and wake some of them up. So that's a whole lot more work than saying lock equals 0. Right? So now whoever was doing some, they're accessing a lock that really isn't congested, it gets slowed down by a lot. Okay. So the slow, fast path because of release. Yeah, let's leave that one the way it is. Actually, let me just call this a wait lock. I think there's another queue lock can mean something else too. We'll do that separately. Okay, the next one I think is really cool. It's called a ticket lock. Anyone hear of a ticket lock? So here we don't use the compare and swap. We use the atomic increment instead. So the idea is for acquire, my ticket equals global ticket plus. And then also, let's see, what is this called? Yeah, this is fine. And then we say while next ticket is not equal to my ticket. That's your acquire. And then your release just like that. So here we need an atomic increment for this one, so I should be a little more clear about that. Let's say atomic inc global ticket. So global ticket starts at 0. You've probably used a ticket lock in the past, but not in software. Maybe you've been to, say, a deli counter. You take a ticket and then you look at the wall until the number comes. That's exactly how a ticket lock works. Except whoever's holding the ticket, when it's their turn, they then get to also push the next ticket button. There's no operator. Right? This is all a bunch of threads trying to coordinate. All right, so what do we think about this one? Yeah.
Is the next ticket also in the atomic include?
Doesn't need to be.
Because it's a release.
Yeah, because we are essentially in the critical section until it's been incremented. So no one else can increment the ticket. So any advantages?
Do you need an atomic compare for the next ticket?
Nope. It will.
Because there's only ever one person that's gonna.
So we're not doing anything after. We're just waiting for the ticket to change, and it doesn't change. If it's my ticket, it's not going to change until I release it. If it's my number. So it's the same number of atomic operations, I suppose. Or? If we want to compare, say, a spin lock. Yeah, let's forget about the wait lock. It's kind of lame. Spin lock is cool, and the ticket lock is very neat.
So fast pass is the same as the spin block.
Yep, and the fast pass is the same, because then the next ticket is my ticket. In fact, I didn't do the initialization, but the global ticket starts at 0, and next ticket starts at 1 naturally. Ooh. In fact, in that case, to be correct here, atomic, yeah, okay, that's good. As long as atomic inc returns the new value, we're good. Yeah.
Is the slow pass faster because you don't use atomic instructions?
Yeah. Okay, so the slow path is a lot more efficient. For a single thread, we only use one atomic instruction. That's nice. But it's not that, atomic instructions are slow, but if we're anyway waiting, what do we care? Like if we run a slow instruction or a fast instruction while we're waiting, pretty much the same. But there's something else that makes this much more efficient. Or can make it at least much more efficient. So if we go back to this thing,
Next ticket's what's in a lock.
sorry, what was that? Okay. So now there's 2 of these variables, right? Let's put them on different cache lines. If they're on the same cache line, well, then it's not such a big difference. If they're on different cache lines, now whoever's trying to acquire a lock, they need the global once. Right? So we always get to acquire, we always get to get a ticket in just one operation. So to get the ticket, it's this global thing moving around. And then we want to see what is the next ticket. We don't need to write to it. Right? So now we have all of these threads. They need to read the next ticket. But the moment someone tries to increment it, it can invalidate all those copies and increment. So invalidate means it sends a message everywhere saying it's my turn. I'm going to update this. So the reading is fast because you get to have copies. It's read only. It's called a shared state cache line. Everyone gets their own copy. But then the writing gets efficient because it can just invalidate everything, do one update, because it's in this. It knows that it was read only before. And there's one more thing, I suppose. There's never any fighting over who's going to write to it. Right? It's always only one thread can do the writing next. So we do have less congestion. Less congestion. But it's still pretty heavy because there's a lot of copying of this. Everyone's reading this next ticket all the time. So there's a lot of that work going on. Okay, a disadvantage, we're still spinning. So there's no waiting here, right? So now we're wasting CPU again, spinning. Any other advantages or disadvantages?
Proper queue is not fair.
Yeah, this one is a proper queue. Whoever gets a ticket first, like, well, it's a first come, first serve. Right? So, first come, first serve. Queuing. Yeah.
How scarce are the cache lines? Because that just adds another one.
Oh, how scarce are cache lines? That's a good question. Anyone have any idea? Unfortunately, scarcity is a function of supply and demand. Right? So we can't directly answer the question, but because it depends on the application. But let's say just how many cache lines are there? Any ideas? There's 3 levels of cache in a normal multi-core CPU, L1, L2, L3. The L3 is enormous. It'll be, on this one maybe it's 4 megabytes. On our big machines it's like 64 megabytes. So it's huge. But it's about as fast as RAM too. I mean, it's a little bit faster than RAM, but not much. So the caches that matter are the L1 and the L2. The L1 on machines I've seen recently, 8 kilobytes. So let's see, 8,192 divided by 64, 128 cache lines. So probably it's not a big deal, because this thread is monopolizing the CPU. Right? It's really waiting for this to get done, so it's okay. Right, and then there's the L2 cache. It's probably not so relevant for locking, but that's say 256 kilobytes. So 4,000 cache lines, 4,096. So there's plenty of room in the caches, really. Okay. Still a lot of congestion on the reading side. On the next ticket, there's no congestion really on the global ticket. No matter how many threads you have, they only ever access it once. On the other side, you have all this everyone trying to get their own read copy, but it's relatively more efficient. I think an update request for a cache would supersede the reads, so it would kind of happen relatively quickly. Let's see, I think I had a plot for this. Maybe I can dig it up immediately. Okay, here, ticket. Let's see. So the spin lock we were talking about is this, test and set. 7 million. Ticket, slower. But then, yeah, you see, as you add more threads, the test and set is horrific. It's really, really a bad idea. Another one is called test and set. It's a kind of a strange one. Let's try that one. Let's briefly talk about that one. So here, this is test and set. So a test and set spin lock. It goes like this. If lock is available, if atomic lock is available, critical section. We'll go like, maybe say it like this. Ooh. Ah, okay. Yeah, okay. So it'll be like this. While lock, while true. Do it like that. Okay. So the general idea here is we first test with a normal operation. And this is just a read. So then we can work with copies. The line is in read only, very nice. But if it looks like it's available, then of course if we want to take the lock, we have to try to grab it with an atomic operation. So then we got it, and then we can execute a critical section. If it looked like it was available and wasn't, which will be relatively common, if you have many threads, it'll still be pretty common, then this will fail, and then we can go back out again and try again. Well, so most of the time, when the lock is not available, we won't do that atomic operation. The difference between an atomic operation and a normal one, a normal read here, is that it can operate in shared state. I can take a copy of this cache line from my neighbors and see that, no, it's still taken. So test and set in our experiments here show that it's much better than test and set. It's like 5 times better, but it still sucks. And then we have mutex, which does test and set and wait. We try a little bit, and then if it doesn't work out, then we wait. That helps us scale a lot more, because now there's just less congestion on this cache line. So whoever's awake, as you said, it's unfair, but whoever's awake, they will get the lock a lot. Right? And the rest are just sleeping until the others are done, until they kind of, in this case, stop running the benchmark. Right? They're all supposed to do a million operations. Couple of threads do their million operations, and then it moves on to the next one. So you kind of get these big batches of threads. Well, one thread doing a big batch of work back to back. Okay, what else do we have here? The next more interesting ones. Yeah, okay, ticket lock is the one we're talking about. Good. So you see, ticket lock is actually most of the time doing better. There's some interesting effects here, because as you pass over 64 hardware threads, now we're using hyper-threading on all the cores. So based on this illustration here, there's actually more of these. There's 2 more sockets, and then in total 64 cores. But on every core you can run 2 threads. So after 64, now we start reusing the cores and having more hyper-threads. So that kind of gives Ticket a little bit of an advantage again, because we kind of stay within a core a little more. But either way, Ticket lock appears to be better than the more naive other locks. So that's nice. But there is a disadvantage. And I think that shows up maybe here. Not exactly sure why it doesn't show up as much as I had expected, but basically with the ticket lock we do not get to sort of optimize the order. Ticket lock is enforcing fairness, first in, first out. And so if that order says you have to go like this, back and forth, ticket lock will do that. There's no other way. Whereas with a spin lock, you can spend all your time in here, and eventually some randomness in the system will say, okay, fine, let's go over to the other socket. Randomness or other policy, right? But at least in the design of the spin lock, it could actually stay on one socket forever. And in Ticket, that's just not going to happen. So it ought to be less efficient in that sense, but it spins much more efficiently because it has these 2 lines. And it only reads. Okay, so that brings us, I think, let me see if I have a little cheat list here. Okay, that brings us to the queue-based locks. Actually, let's. I need to read up on this, but the H ticket is a hierarchical ticket lock. I believe what's happening there is you have two tickets, or in some way or another, there's two tickets. The H ticket lock tries to keep the sort of FIFO order within one socket, but then travels across between sockets a little less often. That's the intent of the policy, but I don't know how it's implemented. So I think we see a benefit to that. Not really. Well, no, in this for this silly I++ benchmark, at least, it doesn't seem to be any advantage. There are certainly advantages if you have larger data structures where they also occupy cache lines that are going back and forth. But in this case, there's just an I++. Okay, and then finally, there's a couple of locks that do much better, right? The MCS and the CLH lock, and they pretty much operate in the same fashion, so we'll just sort of treat them as one in this case. So we'll see how that works. Let's see, I'll put it here. Queue-based locks. So here the idea is we don't have, it's a little bit like the ticket lock in some sense. You get in a queue, like with a ticket lock, but there isn't a shared variable that we're all spinning on even. So the problem, if you recall, the problem with the shared ticket lock, or with the ticket lock, is this. We're all looking at this shared variable, and it keeps changing, so there's a lot of traffic because of it. In the queue-based lock, it goes add my item to end of queue, and then while my item something like that. Okay. Actually, let me see if I can enqueue my item. That's much better. All right. So here the idea is we can add. Okay, good. I'm almost missing a key piece here. Atomic enqueue my item. So here we somehow magically atomically add an item. An item is just a struct queue item. All right. Ooh. My item. So that's allocated on a stack most of the time. It doesn't always work, but for example, you can allocate this item on the stack. You enqueue it to this queue that is there for this lock. So maybe we go lock.queue my item. And then we just wait until this field in my item becomes a 1. It starts out a 0. So now you can imagine how the release goes. Actually, anyone want to take a stab at it?
From the first item in the queue, you just set that the value.
Next item equals pop. Yeah, let's do DQ. Yeah, this is not actually that good because this gets freed up as you return from acquire. So really we have to do the item outside. And this is a problem with queue-based locks. So if we have our function that's doing the acquire, it would go more like this. Right? Because otherwise we have the problem, if we allocate it on the stack here, after we have acquired it, we now release it, and that will make it
Also, following items in the queue are not.
I think those references are not
we-
valid anymore.
yeah, our queue is not necessarily safe. We're probably losing some pointers along the way. Okay, so why is this better?
Don't have too fast as many shared memory around.
Because we're only, I mean, for a given thread, it's only looking at its own variable.
Yeah, exactly. Everyone has their own variable that they're spinning on. A release just assigns to this one variable. In fact, there's two, right? The DQ will remove something, like the tail of the queue will be changed. And then the acquire, it needs one atomic operation. It needs to add this item to a queue, but it's always to a new place. Right? So at least on average, or if we're lucky, maybe we say that. If we're lucky, our atomic enqueue works the first time. So we don't need to try and try. Sometimes it'll be more like an atomic increment. Like we might end up getting the cache line and it turns out it wasn't our turn and we have to retry. So a little bit of that. But basically there's very little congestion on the lock parts of the lock here. So okay. Very low congestion.
It's also faster than a spin lock for a wait. I mean,
Faster than a spin lock.
in that, when you're acquiring, you don't have to wait to acquire the lock itself, right?
Well, this is where we wait to get the lock.
Yeah.
We should probably look at how an atomic enqueue works in order to fully understand this. Let's take a look at that. So, let's see. It's probably like an int go and queue item next. And then we'll have to have a tail and a head, right? Because we want to add things to the head and pull them from the tail or vice versa. Okay, so to add something to the queue, atomic enqueue, we basically want to, let's see, which way should we do it? Let's put it at the head. Whenever we add something, we put it at the head of the queue. So now we need to make a new item. Actually, we're provided the item. We don't have to make it. So we say item next equals head. And then we say head equals item, right? What do you think? If we ignore the stuff with the tail, there's going to be something when the head meets the tail, I think, something we have to deal with. But let's not worry about that. There's an error here.
Go field isn't initialized.
Oh.
It's just not atomic.
Let's not worry about the go field. Yeah, the problem is that it's not atomic. Right, so what could happen is we're reading the head, but then before we make ourselves the new head, someone else read the head, and now we're lost. No, they're lost, in fact. We should draw this to make sure it's right. So we have head. Item 1. Item 2. So item 1 says, okay, that's the head. Beautiful. And then item 2 says, oh no. Oh, it's not that's the head. My next is this, right? That's what we're saying. That was the code. We say the next equals that head. And then we want to reassign. So actually this should be more like item 3, item 0. That's good. We had a head pointer. Okay, this is more like it. So it used to be like that, with these two unassigned. And then these two, at the same time, because of this unfortunate race condition, they both assign their next to item 0, and then they both assign head to themselves. So we assign like that. But then when you make the assignment, there's only one assignment, one value. So I make the last assignment, and that's over. And now this one's lost. It will never be dequeued. Doesn't it have to be probably needs to be a doubly linked list even. If we're going to pull stuff from the tail, how do we go back from the tail? I think that this has to be a doubly linked list for this to work. Anyway, let's make it a stack for now. So it's a LIFO. It's a last in, first out. But anyway, so now we want to pull something off of this guy. We cannot go from the head to here. With the tail, there's going to be something more. And I haven't really thought about that before. Okay, so in order for this to work, we need to use an atomic operation. We can't very well use a lock. I mean, that would be nice. If we're implementing a normal queue, we would grab a lock on the queue, do our assignments as we please, and we're done. But here we're implementing a synchronization operation. We can't use sync operations, except in the wait queue case. We don't really use sync operations to implement sync operations. So what can we do? How do we make this atomic? We have two operations to choose from: atomic increment or compare and swap. And these are pointers, so maybe atomic increment isn't so hot. So let's go with compare and swap. So it's going to have to be a while loop. I'm going to make it a do while, I think. Right? Because we have to try again. That's the whole point here. If something fails, we'll try doing it one more time until it succeeds. Just like with the spin lock. But what's the condition? Yeah, so we're saying, right. So I'll write it out in English because I'm still not sure about the order of these things. But if we say if head is equal to item next, set head equal to item. There we go. right? So this operation, that's what compare and swap does, right? We say this is the value that we want it to still be. No, here. So previously we've used it like, oh, if it's not set, you know, if it's not locked, then lock it. Now we're saying if it's still the same head, well then let's give it a new head atomically.
It's still the same. Why do you have to reset it?
Oh, that equals item instead of item next.
Right, but oh, I see.
So here we said, okay, my next one's going to be the head. Right? My item will be pointing to the head.
Didn't you just assign head equals item before that while condition?
Sorry. Right, so we're initializing the next element under the assumption that this actually was the head. We're not sure about that, so now we make sure. When we make the last assignment here, we make sure that in fact it was. This is actually common in lock-free data structures too. You make a lot of, you do all the long work, you add your list to, you prepare your entry for adding to a list or something like that, and at the very end you do a compare and swap to kind of make it final, to put it in there. In this case, we nothing has happened until we assign a new head. Right? Nothing's happened to the queue until, or in this case, the stack, until we've assigned a new head. So we are careful about the final assignment there. Okay, so we were thinking about the advantages and disadvantages of this thing.
As fast as a spin lock in the test case, so just those one operation.
Yeah, fast path is slower than spin lock. We are still spinning. And so, you know, that's only good if it's if we don't have something better to do. Is it fair? Actually, with our stack, it's entirely unfair, right? But with a queue, it would be fair. As fair as a ticket lock. There's one other major disadvantage that isn't entirely obvious. What data is heap allocated?
I thought the structure was part of it.
Sorry?
There's a lot of overhead of managing all this.
Yeah, so that's I think that you mean in terms of runtime. So that's the fast path is slower than the spin lock. So if this is a congested lock, then one probably should use MCS or CLH. If it's not a congested one probably should use spin lock. But there's some other disadvantage. If we look at just this, something that's a little bit different about this compared to what we're used to. We have to do memory management to acquire the lock. Right? The programmer has to do extra work here. All the other locks, you just say acquire lock, done. So in this case, it's actually pretty easy, right? You keep it on the stack. But what about if it goes It can be like this too. It's not as common, but it can easily be like that. Now you have a real problem. Right? Now we have to allocate this somewhere else. Where would we allocate it?
In the top column, which would call an NG.
Yeah, if there even is one. If we're doing this in the OS, there isn't a top level caller. We just switched to a different process. And we're releasing the p table in a different process here.
You just have like a static array with like a max size, or is that a bad idea?
Well, it's hard to know what the max size is, right? So yes, you could have a static array. You would have to find it. Like when you acquire here, you then have to allocate out of the static array. And if we're anyway allocating, we can use malloc. So we could we get this off of the heap, right? Sometimes a static array is a little faster. But that brings us to a new problem. If it's let's have this global array that we're allocating from. How do we allocate from a global array? This is a shared global array.
It's gonna fault on write and make a new space for it because it's all initialized to zeros, right?
Well, that's not the problem. The problem is it's a shared data structure. We have to have a lock on it. This is a real problem. So, yeah, what you end up with is mallocing, and then malloc has a lock inside. Spin lock, hopefully. Hopefully not an MCS lock, because then it's over. In the general case, there doesn't seem to be a good solution to it. There's cool mallocs that have separate heaps for different threads, and that makes it a lot faster because you don't want to have a lock. Every time you malloc, have a shared lock, you see all this congestion, right? Now, malloc, we use it all the time. Yeah. So, as far as I can tell, MCS is not used outside of very special applications or in like lock research papers, because the memory allocation is far too hard. Okay, or maybe we say requires memory management. Yeah. Okay. There's another kind of lock, since we're actually sort of running out of time, and that's fine. I think we'll spend another. My next lecture will be on the alternatives to this, which is the stuff I'm presenting in China on Monday. But after that, we'll talk about sort of the problems of synchronization, sort of in a separate lecture on next Thursday. That's fine. I wanted to introduce one more lock, which is pretty cool. It's called the reader-writer lock. So here the idea is allow concurrent readers. Or one single writer. So this is pretty nice, right? If you're, say we have a tree, we're trying to find a key in the tree. It takes a little while to go through it, but we're just trying to look for it. Then we could have multiple threads doing this traversal of the tree at the same time. It gets nice and fast. But then for consistency, whenever you try to add something to a tree, it gets pretty complicated. You don't want two threads modifying the tree at the same time most of the time. At least not for a balanced tree. I don't think I've seen a good solution for that. Because you add something to one part of the tree and then suddenly everything ripples over, and it gets very hard to do that concurrently. So in a reader-writer lock, we somehow want to allow, if it's just readers, we allow many of those. We don't allow any readers if there's a writer in there. And if there's a writer in there, well, then we also don't allow any other writers. So then it'll be a read acquire and a write acquire, and a matching read release and read write release. Okay, so in this case, if I recall correctly now, it goes, we have a lock for writing and for kind of entering a reading critical section. So you say acquire inner lock, or call it the writer lock. And then we increment the number of readers and release writer lock. And then for the write acquire, it goes acquire writer lock if reader is greater than 0, release writer lock. And return while let's see, I guess we'll do it like this. While true, this will work. Acquire the writer lock if there are readers. Try again. And otherwise break. Right. There's probably many ways we could have written this. But so here, basically we're not holding the lock for the whole traversal of the data structure. We're just holding it briefly to say how many readers there are. So now we allow multiple readers. And on the read release, it's the same thing. We now have to acquire the lock, decrement the reader count, release the lock. So there's some extra work in there, but you can have some real advantage in terms of concurrency. So I guess I would put a reader-writer lock in the same category as a try lock. It's sort of a exotic lock that doesn't do what locks usually do. There aren't that many of those. Yeah, I guess that's it for today. So yeah, next time I'm not here, will be posted on Tuesday, hopefully. And then on Thursday, we'll talk about difficulties in synchronization as opposed to how we implement synchronization operations. Any questions? No. All right, good. I'll have a good weekend, and I'll see you next Thursday then.